Welcome back, class. So as a reminder, what we did last time, we talked about the construction of the projective space P2 of R. We added a bunch of points to R2 to make it so that every pair of lines, including parallel lines, intersected at a point, like the cards in a spotted deck. In this video, we're going to look at the second problem, which is that if I'm talking about R2, the size of that set is enormous, and I really want to replace the R with something else. So today we're going to talk about the thing I'm going to replace R with, which is something called F7. But I'm also going to talk more generally about all the finite things that we could replace R with, because I want to also let us start having a conversation about what if instead of making a 57-card spotted deck, we wanted to make a spotted deck with some other size with, say, 14 symbols per card. Could we do that? What would that require? And this kind of thing. So this leans on a little bit of stuff that I'll summarize from abstract algebra. And so today we're just going to talk about fields. And then in the next video, we will actually officially put these two videos together. We'll talk about projective space over a finite field. We'll officially make P2 of F7. And it will turn out that P2 of F7 basically is equivalent to our 57-card spotted deck that we've been trying to make. And then we can start asking questions about what other spotted decks we can make. So that's the plan. Today, we're going to talk about fields. So what is a field? This is a really daunting definition if you have not seen it before. So this is something that you'll see in abstract algebra if you take that. But basically, what do you need to know? A field is a set, which I'm going to call F. And in that set, you know how to add, and you know how to multiply. And basically, everything else on this page says that addition and multiplication behave in ways that you would expect. So, for example, there's some number called 0, and if you add 0 to something, you get that something. And then for everything, I could also subtract it. And if I add, it doesn't matter what order I add in. And if I add things, I certainly don't need to bother about parentheses. And so these four are all statements about how we expect addition to work. And then there's a similar list for things about how multiplication works. So namely, we also have an element called 1 that you can multiply by anything and get that thing back. Also, I'm specifically insisting in my definition of a field that 1 is not equal to 0. This, sometimes people will insist that, sometimes not, but I definitely am insisting that 1's not equal to 0. And then there's another operation called inverse that you can make where if you take something's inverse, then if you multiply it by its inverse, you get 1. Note, you cannot take the inverse of 0. Again, just like in real life. Okay, and then we have multiplications, also commutative and also associative, and so these are a list of properties that one can assume for multiplication in a field. And then last we have this distributivity property, which is how you relate multiplication and addition. So again, I've broken this down for you into a set of properties of addition, a set of properties of multiplication, and a statement about how multiplication and addition are ultimately related to each other. I'm not going to prove a lot about this, and I'm not going to use a lot of these axioms, but I want to officially define what this means so that if you want to give precise meaning to the theorems that I tell you about, you can come back here and look at them and you could really see, okay, I'm really claiming when I say that there's a field with 7 elements or that there's not a field with 22 elements, that I'm claiming something very concrete and specific. But let's start with F7. And so what is F7? Well, the F stands for field, and so F7 stands for the field with 7 elements. And what are those elements? They are 0, 1, 2, up to 6. And I'm meant to be able to both add and multiply these numbers. So that means that I should be able to fill in for you a table of what happens if you multiply or add these numbers. Okay, so when I add 0 to something, I actually know exactly what happens. So 0 plus 0 is 0, 0 plus 1 is 1, so on and so forth. And then I can keep going down here. Okay, so then what's 1 plus 1? Well, 1 plus 1 is 2. No big surprises there. In fact, if I go across this table, 1 plus 2 is 3, 1 plus 3 is 4, 4 is 5, 1 plus 5 is 6. And now, here's an interesting question. What is 1 plus 6? And so, if you've never seen this before, then of course your brain is inclined to say, oh, well, 1 plus 6 is 7. Except it can't be 7, and here's two different reasons why it can't be 7. One is it can't be 7 because 7 is not an element of F7. And any two elements in F7 that I combine by addition or multiplication, I have to get back an element in F7. Here's another reason, though. One of my many axioms, which I do not expect you to remember, but one of them is that every element has an additive inverse. That is, there's something I can add to 1 and get 0. But notice, so far in this whole row, nothing has gotten me 0. Which means that if I'm going to follow the axioms, I absolutely have to put a 0 here. And if you think about that, 1 plus 6 equals 0, you probably think this sounds a little bit familiar because this actually sounds a little bit like arithmetic mod 7. And so really, that's all the operation in F7 is. Everything in here is just happening mod 7. And so this is a complete system of representatives of the equivalence classes mod 7, or whatever technical mumbo-jumbo you want to think about it. These are the 7 things mod 7 is how I'm going to think about it. So then you could fill in the rest of this table. So I'll go ahead and fill this in. 6, 0, 2 plus 6 mod 7, for example. 2 plus 6 would be 8, but mod 7, that's 1. Namely, that's the remainder of 8 when I divide by 7. And so that's our addition table. This just tells me, hey, if I add 4 and 6, what do I get? I get 3. Conveniently, that's so because 4 plus 6 is normally 10, but I need to mod that by 7, which gives me a remainder of 3. Likewise, we should write down a similar table, but for multiplication. Okay, so the first thing we can do is, what happens if I multiply something by 0? Well, I get 0 and then I mod it by 7. What's 0 mod 7? It's 0. So that gives me a super easy row and column to fill in. Likewise, I know exactly what happens when I multiply something by 1, because one of my axioms is that when you multiply something by 1, you get that thing, like that. Okay, and everything else I'm just going to fill in by doing the math mod 7. So here is our complete addition table and multiplication table for the field F7. And if you are very determined, you could now check that every axiom I claimed is true for this way of adding and multiplying. And so if you were a computer, I could just give you these two tables and you could calculate every possible sum and product that you want. Now, you might try and check some of the axioms, such as everything has an additive inverse. That means everything, there's something you can add to it that would give you a 0. So that should say there's a 0 in every row, which I can check, not so difficultly. Slightly more difficult, everything's supposed to have a multiplicative inverse except 0, which does not, which means there's supposed to be a 1 in every row, so that is a little bit more exciting. So there's the 1, 1, 1, 1, 1, 1. There are my 1s. Likewise, the same thing is true about columns, so you could check that every column, again, except for the 0 column, has 1s. It's a bit trickier to check things like the claim that this thing is associative, but the thing I really want you to pay attention to most is that really this worked out so that everything had multiplicative inverses. And so I'm allowed now in this field to calculate all sorts of things. So if someone wants you to calculate in F7 For example, the number minus 2, well, that would be the thing that is the additive inverse of 2, right? That's what minus 2 means, is the additive inverse of 2. So that's the thing that I add to 2 to get 0, which I see here is 5. So minus 2 in F7 just is 5. Likewise, 1/3 in F7, that would be the thing I multiply by 3 to get 1. So I will see, reading across the table here, that 1/3 is 5. And so if I wrote down something like 2/3 in F7, well, that is 2 times 1/3, which is 2 times 5. And 2 times 5, I can look here and see it is 3. Now, it might not be obvious how you would actually think about this question if you didn't have in front of you this giant table, but you can actually just think through the elements and think, what do I have to multiply 3 by in order to get 1? And if you try things, eventually you'll come to, okay, 3 times 5 is 1 in F7. That's what 1/3 means. And so basically, the point of all of this is all the sorts of things that you could write down with real numbers, addition, subtraction, division, all of these sorts of things, you can write them down in F7. But F7 has the humongous advantage over the real numbers that it is much simpler, because instead of having uncountably many elements, it has 7 elements. So here's a big theorem that concerns why everything we did just worked. Namely, if P is prime, then the integers working modulo P, and that's all this means, is the integers where the operations happen mod P, is a field. And we denote it by FP, of course. So likewise, if instead of 7, I had chosen 11 or 17 or 29, all of those would also have given me fields by exactly the same thing. Just instead of working mod 7, work mod 29, and instead of using the numbers 0 through 6, use the numbers 0 through 28. And everything works out in the same fashion. Of course, if you want to write out this table and I replace the 7 with a 29, then it's much, much bigger. Now, I want to point out something important here that is a source of potential confusion, especially with what I'm about to say. But I want to point out, if I try this construction with something that's not prime, it's not going to work. So z mod 4z is not a field. Why not? Well, let's try and write down our multiplication table, just like we did here. Note this is going to be much quicker, because now there's only 4 things. And already that's telling me this isn't a field. Why? Because remember, everything has to have a multiplicative inverse, except 0. That is, every non-zero element, I have to have something I can multiply it by to get 1, which, remember, translated in the table to us saying there's a 1 in every row. Namely, that 1 tells me the thing I have to multiply, for example, 2 by in order to get 1. However, if you look closely, I mean, it doesn't even have to be that closely, it's not a very big table, at this table, you'll notice this row, it's not the row corresponding to 0, but it does not have a 1 in it. And so what that means is 2 does not have a multiplicative inverse. So this is because 2 not have a multiplicative inverse. And so, oops, this thing's not a field. In fact, if you want the terminology, Z mod 4Z is what's called a ring, which is to say that it satisfies some of the properties we would hope for a field to satisfy, but it doesn't satisfy all of them. And so, in particular, we can't do anything that we're about to do with Z mod 4Z. And so, in fact, if you try and pick something that's not a prime, it will never work. So, in fact, actually, theorem Z mod NZ is a field if and only if n is prime. Now, please note, I am emphatically not proving any of these things that I am calling theorems in this section about finite fields. I am just sort of giving you a brief overview of the facts about them that we're going to mention. And really, the only thing we're going to need at the end of the day in order to make our spot it deck is this. As long as you're comfortable with this, you're going to be able to make the 57-card spot it deck. You'll be happy as a clam. But I want to talk a little bit more about how this fits into the bigger picture. So I'm going to tell you a little bit more about finite fields. So this integers mod n business, where I add and multiply mod n and take the numbers 0 through n minus 1, that only gives me a field if n is a prime. So why did it not work for 4? 4 is not a prime. I know that's not super profound. But that might raise the natural question, okay, so does every finite field just have a prime number of elements? And the answer to that turns out to be no. And so here is a more nuanced theorem than either of the previous ones, which is there exists a field with n elements, if and only if n is p to the k with p prime. So in other words, if you are looking at a prime power, then there's always a field with that many elements. And if you're not looking at a prime power, there's not a field with that many elements. So there's no field with 6 elements, there's no field with 12 elements, and so on. And so a lot of times in math, you'll see theorems that sort of sneakily have a hypothesis that something is a prime power in them. And that hypothesis that something is a prime power is almost always coming back to this theorem. So this theorem is a very important theorem in mathematics, and it's going to show up a lot in our coming discussion of other spot it decks. Okay, namely, we're going to see this hypothesis about prime powers occurring, but it's not exactly going to be on the combinatoric side of things. You'll see what I mean when we get there. But anyway, just know you can produce a field with n elements if n is a prime power. It's well known how to do it. In fact, you can add to this theorem that that field is essentially unique. You have to decide what essentially unique means. But if you do, then this all works out. So there's one field with 49 elements. That's it. Aside from renaming the elements to be different things. So let me just, again, to solidify these ideas, I want to show you what the field with 4 elements looks like, just so that you'll be very convinced that the field with 4 elements is not the integers mod 4. So it's got an element called 0 and an element called 1. which you might recall, it was an axiom that every field has an element called 0 and an element called 1. But I'm going to be more creative with my other elements. I'm going to call my other elements omega and omega plus 1. So these are my elements. And like before, when I said with F7, all you really need in order to know how to work with the field and to verify that it's a field is this table. I'm just going to write down the corresponding table for F4. Now here, I gave you the helpful, very, very, very helpful trick that, hey, this is all addition and multiplication mod 7. For F4, I'm just going to write it down and show you, and you can try and guess what the rule is, or try and simplify the rule so that you could reproduce the table, or you can just take my word for it and just use it as it is. So here is our addition table. The one square I will sort of call your attention to here, and this sort of gives away everything that's happening, or not everything, but a lot of what's happening, is this square, where what that says is that 1 plus 1 is 0 in this field. And what that tells me, I mean, aside from everything else here, is that this is not really a mod 4 thing, because mod 4, I'd have to add something to itself 4 times in order to get 0. Here I added 1 to itself just once, and I got 0. And so what that's telling me is really I should think of this thing as operating mod 2 and not mod 4. And so if you want to interpret this, actually, basically everything from this follows from the idea that mod 2, or that everything's happening mod 2. So for example, omega plus omega is also 0 because that would be 2 omegas and 2 is 0. Okay, and then we have to do multiplication. Okay, and so here's our table for multiplication. This one is definitely much more mysterious if you've not seen this before, because I have things like, omega times omega plus 1, that works out to be 1, which is probably not exactly what you would expect. But anyway, this all sort of gives you some idea as to what's going on. So here is a field with 4 elements. And so my point here is not so much that you need to memorize this, because you definitely don't need to memorize the field with 4 elements as a multiplication table. But someone could tell you for any prime power how to make one of these things. But here's the summary, executive summary of what we need to know for everything that we're about to discuss. So here's what we actually need to know. We need to know that for p prime, this thing I've called fp, which is the same thing as the integers mod that prime, is a field. And we need to know how to add and multiply and divide and everything in this, this field. So for example, if I ask you, what is 3 inverse in F17, you have to be able to think about it and eventually give me the answer as to what 3 inverse is. So what is 3 inverse in F17? Well, 3 inverse in F17 is 6. Because 3 times 6 is 1. And 3 inverse is just the thing that you multiply by the number to get 1. So similarly, 6 inverse is 3. And if I wrote you down something like, what's 2/3? Well, 2/3 will be 2 times 1/3, so 2/3 would be 12, and so on. So we have this. For any p prime, we know exactly how to work with a field with p elements, and we can write it down. We need to know that for n not prime, z mod nz is not a field. We need to know for n equals p to the k, that is for n a prime power, someone other than us, someone else, knows how to write down a field with p to the k elements. So that's if k is 1, even we know how to write down a field with p to the k elements. But if p is bigger than 1, so if p is, say, 25, or sorry, if n is, say, 25, that would be 5 squared. Someone, but not us, knows how to write down a field with 25 elements. Okay, and that's what these two together say. Z mod 25z, definitely not a field with 25 elements. There is a field with 25 elements. People know, you could look it up online, it's not a secret, but it would not be productive for us to go into how to actually make it. And then, lastly, for no other n, does a field with p to the k elements exist? So no field with 6 elements, no field with 10 elements, no field with 105 elements, and so on and so forth. So we know exactly when there is a field with p to the k elements, and if k is 1, we know what that field is, and we know how to perform the operations in it. And that's what we're going to need in order to make our Spot It deck with 57 cards using F7 from this video and using this idea of a projective plane from the previous video. But for now, I'll leave it there. Until next time, be well.